Hello everyone. This is Chi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Welcome back to our Deep Learning course. Today, we're continuing Chapter 5, Classic Convolutional Neural Networks 3. NDR focus is Part 5.3, VGG, a model famous for its deep and simple structure, which is still influential in computer vision. Let's start with VGG's network structure, then apply it to a bird classification task. First, let's get to know VGG. It's a deep convolutional neural network developed by the Computer Vision Group at Oxford University and DeepMind. VGG has a total of 6 types of network structures. You can see them on the slide, and they get deeper from left to right. The bold parts mark newly added layers. A core feature of all VGG structures, they all include 5 groups of convolution operations. We can call this 5-stage convolution feature extraction. Each group has several convolution layers, and after each group, there's a pooling layer. This convolution group plus pooling structure is very regular, easy to understand and implement. Among VGG's 6 structures, VGG-16 is the most widely used. Its name means it has 16 weight layers, 13 convolution layers, plus 3 fully connected layers. Let's break down its structure, step by step. Input layer, 224, multiplied by 224, multiplied by 3 color images, standard for large-scale image tasks. Group 1 to convolution layers, 3 multiplied by 3 kernels, 64 channels each, stride 1, same padding, ReLU 1 max pooling, layer, 2 multiplied by 2, stride 2. Output after pooling, 112 multiplied by 112 multiplied by 64. Group 2 to convolution layers, 3 multiplied by 3 kernels, 128 channels each, same max, pooling. Output, 56 multiplied by 56 multiplied by 128. Group 3 convolution layers, 3 multiplied by 3 kernels, 256 channels each, max, pooling. Output, 28 multiplied by 28 multiplied by 256. Group 3 convolution layers, 3 multiplied by 3 kernels, 512 channels each, max, pooling. Output, 14 multiplied by 14 multiplied by 512. Group 3 convolution layers, 3 multiplied by 3 kernels, 512 channels each, max, pooling. Output, 7 multiplied by 7 multiplied by 512. Output layers, flatten, turn 7 multiplied by 7 multiplied by 512 into 25088 dimensional vector, 2 fully connected layers, 4096 units, each one fully connected layer, 1000 units, for ImageNet's 1000 classes. Every step's dimension change is regular. This is VGG's biggest advantage. Let's match the structure we just talked about with the diagram on the slide. The symbols here are easy to understand. Convolutional layer plus ReLU. Each small blue block represents a convolution layer followed by ReLU activation, exactly the convolution layers in each group. Max pooling layer. The green blocks are the max pooling layers after each convolution group, 5 in total, 1 per group. Fully connected layer. The orange blocks are the 3 fully connected layers, 409, 6409, 610, 00. Softmax. The final layer that converts fully connected outputs to class probabilities. This diagram visually shows VGG-16's convolution group pooling fully connected flow. You can clearly see how data shrinks in size but increases in channel depth step by step. Now, let's use VGG-16 for a practical task, classifying bird species from the California Institute of Technology's bird database. First, data preparation relies on Keras image data generator, just like we did with AlexNet. Set im size equals 224 VGG's required input size. Training generator, train generator equals image data generator, rescale equals 1/255. Flow from directory. Rescale equals 1/255 normalizes pixels to 0 to 1. Target size equals 224,224. Resizes all images to 224 multiplied by 224. Batch size equals 100 reads 100 images per batch. Class mode equals categorical uses one hot labels. Validation generator, same as training, but reads from the test folder. This generator is key for handling large bird datasets. We don't need to load all images into memory at once, which avoids memory overflow. To confirm the data generator works correctly, we visualize 10 sample bird images. The code is simple. First, use x, y equals next validation generator to get one batch of data. X is images, y is labels. Second, create a 2-row, 5-column figure with matplotlib, adjust height to 6 and width to 15 for clarity. Third, flatten the axes and loop through 10 images. Axi im show xi displays each bird image. The slide shows the result. You can see different bird species with distinct feathers and postures. This confirms the generator is reading the bird data correctly, and we're ready to build the model. Let's look at the VGG16 model structure from the model. Summary, output. This helps us confirm the model is built as expected. Input layer, input 2 has shape, none, 224, 224, free, batch size, arbitrary, 224, multiplied by 224 color images. Convolution layers, for example, Conv2D. First convolution has 1792 parameters, 3 multiplied by 3 multiplied by 3 multiplied by 64 plus 64 biases, and outputs 224 multiplied by 224 multiplied by 64. Conv2D 3 Group 2's first convolution has 73,856 parameters, 3 multiplied by 3 multiplied by 64 multiplied by 128 plus 128 biases. Each convolution layer's parameter count follows the 3 multiplied by 3 kernel rule. Pooling layers all have 0 parameters, no training needed, just downsizing. For example, max pooling 2D 1 goes from 224 multiplied by 224 112 multiplied by 112. Output layers, we use global average pooling 2D instead of flatten for simplicity to get 512 features, then a dense 200 layer for 200 bird species and activation. Total params are to 14.8 million. This is VGG's depth, but manageable with modern GPUs. Next, we compile and train the VGG16 model. First, compile, use model VGG16. Compile optimizer equals atom LR equals 0.001, loss equals categorical, cross entropy. Metrics equals accuracy, atom optimizer, with learning rate 0.001, standard for VGG, categorical, cross entropy for multi-class classification, bird species are multi-class, and track accuracy. Second, train, use model VGG16. Fit, generator, train, generator, epochs equals 20, validation, data equals validation, generator, fit, generator is for data generators. Train for 20 epochs, enough for the model to learn bird features, and validate on the test generator to check generalization. To further improve the model's classification accuracy, we can add batch normalization, BN, to each convolution layer. BN works by normalizing the input of each layer, which speeds up training and reduces overfitting. The code is simple. After each convolution layer, or before activation, add x equals batch normalization, axis equals 3x. The axis equals 3 means we normalize along the channel dimension, since our data is in NHWC format, batch, height, width, channels. This small change can often boost accuracy. Try it if your VGG model's performance is not ideal. It's a common trick to optimize deep networks like VGG.